Hello students, welcome to physics class. Today we discuss heat energy produced by the electric current, electric power and electric energy. First let us see what is the heating effect or heat produced by the electric current. For that, here we have a conductor of resistance R. AB is a conductor of resistance R. The end of the AB is connected to a battery of potential V to maintain a constant potential difference between A and B. Say the potential at A and B are VA and VB. The potential at A and B are VA and VB. Say VA is greater than VB. The potential at A is greater than the potential at B. So a current I is flows from A to B. Since there is a potential difference between A and B, the current I flows through the conductor AB from A to B. Now what is the potential difference between the point A and B? The potential difference between the point A and B can write as the potential at A minus potential at B. The potential difference is denoted as V. The potential difference between A and B is denoted as V, where potential difference is equal to potential at A minus potential at B. That is VA minus VB, which is always greater than 0 because the potential at A is greater than the potential at B. Now let us find what is the total amount of charge that flows through the AB in a small time interval t. We are taking a very small time interval t and find what is the total amount of charge that flows from A to B. And we are writing the charge Q is equal to I into T. What is I? I is the current flows through this conductor for a time t. So within that time, we can say the Q is the amount of charge that flows through the conductor. So we can write the charge Q is equal to current into time. Q is equal to I into T. So once the charge is moving from A to B, there will be a decrease of potential energy for the charges because the charge is moving from a higher potential to lower potential. So the potential energy of the charge will change. Usually it will decrease. Now find what is the change in potential energy or what is the decrease in potential energy when the charge is moving from A to B. We can write the decrease in potential energy is equal to final potential energy at B minus initial potential energy at A. The decrease in potential or change in potential is equal to final potential energy of the charge at B minus initial potential energy of the charge at A. We are denoting it by U, the symbol U, the change in potential energy. Say the U is equal to what is the potential energy of the charge at B. We can write the potential energy of the charge at B is equal to the charge into potential at that point. We told the potential at point B is VB. And so the potential energy of the charge here is Q into VB. What is the potential energy of the charge at A? Potential energy of the charge at A is equal to Q into VA. Charge into potential difference. Charge into potential at that point. That's Q into VA. Now potential at B, potential energy at B minus potential energy at A. That's the difference in potential energy or decrease in potential energy. U is equal to Q VB minus Q into VA. And you can write U is equal to Q into, Q is common, we take it outside, Q into VB minus VA. And we are giving with a minus sign, we are taking the minus sign outside this bracket and putting minus Q into VA minus VB. We want to show that the energy is a negative because there is a decrease in potential energy. So this term is negative. It shows that the potential energy of the charge is decreases when the charge is moving from A to B. Minus, the value is minus. That is, the potential energy change is negative. So we can say when the charge is moving from A to B, there is a decrease of potential energy. There is a decrease of potential energy. But remember, by the conservation of energy, energy is always conserved. By the conservation of energy, the decrease in potential energy will be the gain in kinetic energy or the charge. Once the potential energy of the charge decreases, there will be a increase of kinetic energy. The kinetic energy of the charge will increases when it is moving from A to B. So the decrease in kinetic energy, the decrease in potential energy will be equal to what? The gain in kinetic energy. So we can write this gain in kinetic energy is equal to the minus of decrease in potential energy. The minus of decrease in potential energy. Already know the potential energy is negative, a decrease in potential energy. So now minus minus become plus. So what is the increase of kinetic energy? Plus QV. Plus QV. That is the increase of potential energy. Negative or decrease in potential energy. So it becomes positive. It's greater than 0. But you know that when the charge is accelerating, when the velocity of the charge increases, it not gain any final kinetic energy, because when it get accelerated, it collide with the fixed ion inside the conductor and also with the other electrons. So whatever the kinetic energy gained by the electron is lost during this collision. But this kinetic energy is gained by the fixed ions inside the conductor. So what happened? With that energy, they vibrate from their mean position. The amplitude of vibration actually increases. So it produces a heating. When the molecules are vibrating from the fixed position, the amplitude of vibration increases. It produces a heat energy. So when current is passing through a conductor, the conductor is getting heated. So we can say this kinetic energy is actually gained by the molecules or fixed ions inside the conductor, and that actually converted into heat energy. So the amount of heat energy or the heat energy dissipated in the conductor can be write as the H is equal to Q into V, because the entire kinetic energy is converted as a heat. That's heat energy we are writing as heat. Heat is equal to Q into V. That's whatever the kinetic energy is converted into heat energy. So heat energy can be write as Q into V. Another form, the heat energy can write as, we are writing the Q is equal to I into T. Charge we are writing as current into time. So heat energy can write as VI into T. VI into T. So actually this phenomenon we calling as heating effect of electric current or Joule's heating. This phenomenon or the production of heat in a conductor when current is passing through the conductor is known as Joule's heating. So by Joule's heating or by Joule's law, the heat energy produced in a conductor can be write as charge into potential difference, or if you're writing the charge as current into time, we can write as VI into T. VI into T. And if you are writing the V is equal to I into R, substitute V is equal to I into R, now it becomes I square R into T. I square R into T is another expression for the heat energy. Heat is equal to I square R into T. And if you are writing that I is equal to V by R in this equation, I is equal to V by R, another equation we getting V square by R into T. V square by R into T. All are the expression for the heat energy produced in a conductor when a current I passing through the conductor. Now, by using this equation, we can state the Joule's law of heating as like this. According to Joule's law of heating, the heat energy produced in a conductor is directly proportional to the square of current for a given resistance. That is, by using this equation, we can say for a given resistance R, the heat energy is proportional to the square of current. That is, H is directly proportional to I square. The heat energy is directly proportional to square of current for a given resistance R. Now, the heat energy is directly proportional to the resistance for a given current. You can see that if the current I is constant, the heat energy is directly proportional to the given resistance. That's directly proportional to R. The third, it is inversely proportional to, heat energy is inversely proportional to R for a given V. That is, for a given voltage or potential difference, the heat energy is inversely proportional to the resistance. H is inversely proportional to resistance for a given voltage. And the heat energy is directly proportional to the time t for which the current flows through the resistance. When the time increases, heat energy produced in the circuit also increases. That's known as the Joule's law of heating. According to Joule's law of heating, the heat energy is directly proportional to the square of current for a given resistance. Heat energy is directly proportional to the resistance for a given current, and heat energy is inversely proportional to the resistance for a given voltage, and it is directly proportional to the time for which the current flows through the resistance. Now let us see what is the electric power of a circuit. The electric power of a circuit is defined like this way. The rate at which work is done by a source of EMF in maintaining an electric current through a circuit is called electric power of the circuit. You know that in order to maintain an electric current through a circuit, the source wants to expend its electrical energy. The source expends its own energy to maintain an electric current through the circuit. So, the rate at which the work is done by the source of EMF in maintaining an electric current through the circuit is called the electric power of the circuit. Or otherwise, the rate at which an appliance converts electric energy into other form of energy is called its electric power. If it's an electric device, we can define the power of the electric device or appliance like this way. The rate at which an appliance converts electrical energy into other form of energy is called its electric power. Usually, when an electric device works, it will consume the electrical energy, and what is the electric energy consumed in a unit time is known as the power of that electric device. Now, suppose we have a circuit. If I current flows through a circuit for a time t, I current is flowing through a circuit for a time t at a constant potential difference V. Suppose we have a circuit having a resistance R and applied by a potential difference V. Now I current is flowing through the circuit. Now we can say the work done or energy consumed by the circuit can be written as the work done is equal to VI into T. The work done is equal to VI into T. This equation we already derived when you are discussing Joule's law of heating. This is actually the work done by the source to maintain this current. That work is equal to VI into T. This is the total work can write as VI into T. What V? V is the potential difference applied to this resistance. I is the current passing through the circuit, and T is the time up to which the current is passing. So the work done by the source can be write as VI into T. That much Joule. Now the electric power, by definition, the electric power is the rate at which the energy is consumed. So the electric power is equal to the energy by time or work by time. Work done by the battery is actually energy. That's work by time. What is work done? VI into T. VIT by T. So it becomes V into I. That power of the electric circuit is equal to potential difference into current. Power can be written as current into potential difference. And we can rewrite as, if you are writing V is equal to I into R, substitute V is equal to I into R, then it becomes I square into R. I square into R. And if you are writing that I is equal to V by R, I is equal to V by R, we get another form, that's V square by R. All are the expression for the electric power of a circuit or electric power of a appliance. Now, what is the SI unit of electric power? You know that power is measured in watt. So, electric power is also measured in watt. And it is represented by the simple capital W. The simple capital W. The SI unit of electric power is watt. And see, if work done is equal to 1 joule and if you are taking the time is 1 second, work is equal to 1 joule and the time is equal to 1 second. Now we getting that power is equal to 1 watt. So 1 watt is equal to actually 1 joule per second. 1 watt is equal to 1 joule per second. So we can define the 1 watt power like this way. The power of an appliance is 1 watt if it consumes energy at a rate of 1 joule per second. You can say an electric appliance having a power of 1 watt if it consumes a 1 joule energy in 1 second, or it consumes energy at a rate of 1 joule per second. Okay, so actually we told the SI unit of electric power is watt, but for practical purpose we have some bigger unit of electric energy. We can use kilowatt. 1 kilowatt is equal to 10 raised to 3 watt or 1000 watt. 1 kilowatt is equal to 1000 watt or 10 raised to 3 watt. Megawatt, some more bigger unit. Megawatt. 1 megawatt can write as 10 raised to 6 watt. 1 megawatt is equal to 10 raised to 6 watt. And we have a commercial unit of electric power. The commercial unit of electric power is horsepower. Horsepower. Some of the appliances are express their power in horsepower. Example, motor. The power of motor is usually expressed in horsepower, and the symbol HP, horsepower. Now 1 horsepower is equal to 746 watt. The commercial unit of the electric power is equal to horsepower. 1 horsepower is equal to 746 watt. Now let us see what is electric energy. The total work done or energy supplied by the source of EMF in maintaining an electric current in a circuit for a given time is called electric energy consumed in an electric circuit. For that, suppose we have an electric appliance, a bulb or any electric appliance which is connected to a circuit. Say if P is the power of this appliance and which is connected to a potential V. Now, in order to maintain a current through this circuit, actually the source have to expend its energy. So the total work done or the total energy supplied by the source of EMF in maintaining an electric current in a circuit for a given time is called electric energy consumed in the circuit. So if P is the power of this device and if current is flowing, I current is flowing through this device for a time T, we can write the electric energy supplied by this device is equal to, or electric energy consumed by this device can be write as power into time. Electric energy is equal to power into time, and T is the time up to which this appliance is working and P is the power. So electric energy consumed by this device or the work done by this source can be write as power into time. So we already know that power is equal to V into I. Power is equal to V into I. Well, V is the potential difference and I is the current passing through the circuit. VI into T. And if you're writing the V is equal to I into R, we can write as I square R into T. Power is equal to, electric energy is equal to I square R into T. That much joules. And the SI unit of electric energy is joule itself. The SI unit of electric energy is joule. And 1 joule is equal to 1 watt per second. Now, the commercial unit of electric energy, this is the SI unit. SI unit is joule. And we have a commercial unit for the electric energy. The commercial unit of electric energy is kilowatt hour. Kilowatt hour. In that unit, we using instead of watt, we are using kilowatt. Instead of second, we are using hour. That is 1 kilowatt hour. This kilowatt hour is also known as board of trade unit. Board of trade unit or kilowatt hour. And 1 kilowatt hour is defined as the electric energy consumed by an appliance of 1 kilowatt in 1 hour. Suppose we have an electric appliance of power 1 kilowatt and the total energy consumed by the device in 1 hour will be equal to 1 kilowatt hour. So 1 kilowatt hour can write as 1000 watt into 3000. You can write as it is 1000 watt into 3600 second. 1000 watt. 1 kilowatt is equal to 1000 watt and 1 hour is equal to 3600 second. So 1000 watt into 3600 second. So we can write 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joule. 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joule. That's a commercial unit of electric energy, but its SI unit is joule itself. That's all today. Thank you.